Hi, today we are going to discuss an application of linear algebra in economics. It is the Leontief input-output model and its applications. So the Leontief input-output model basically it explains the dependence between the input and outputs of various industries in the economy. It analyzes how an industry undertakes production by using the output of other industries. Basically, it aims to find an equilibrium rate of production for the industries so that it satisfies the demands as well as allows it to be profitable. So let us look at closed system first. This is the equation for the closed system. X denotes the output from various industries. In a closed system, we are assuming that a fraction of the output goes back into the system as the input. That is, the output is used solely to satisfy the input of the industries. That is a closed system. So here the matrix A is a matrix of inter-industry coefficients, and each element in the matrix notes a fraction of output of each industry requires as input by the other industry. So this is an eigenvalue problem where the eigenvalue lambda is equal to 1. So this is an example of the matrix A. Let us look at the electrical industry, that is the second column. Here 40% output from the electrical industry is utilized for coal industry, 10% goes back to the electrical industry, and 50% goes to the steel industry. So here we see that the sum of all columns is 1. This is because in a closed system the output is solely used to satisfy the input only. Now, Perrin-Frobenius theorem. This theorem states that for a non-negative matrix A, there will be an eigenvalue sigma, and there is also a non-negative eigenvector x, such that Ax is equal to sigma x. Here we know that our A matrix is non-negative because it denotes a fractional output that is utilized as input. So we can say that there will always be a non-negative eigenvector x. Coming to an open system, in an open system, there will be an external demand D to the system. So the output X satisfies the input that is AX and also an external demand D. So here we can see that X is equal to I minus A inverse times D. In order for a solution to be exist, I minus A should be invertible as well as non-negative. So the conditions for the existence of an I minus A inverse matrix. So let A be a non-negative matrix, then I minus A inverse exists and is non-negative if and only if there exists a non-negative vector x such that x is greater than Ax. This condition means that there should be a production schedule x such that each industry produces more than it consumes. Coming to the proof of the existence, for an industry to be profitable, the sum of each column of A matrix should be less than 1. Here we have seen that the sum of the columns is equal to 1 because it is a closed system. There is no output that goes to external demand or to the profit. So here for the industry to be profitable, it should be less than 1. This is the condition. So in this case, we know that in matrix form we can write it as A dash times In is less than In, where A dash is the transpose of A and In is an n into 1 vector of ones. On solving this, we know that we'll get a vector where each element is the sum of each of the columns of A matrix or the rows of A transpose matrix. So from this theorem, we know that if x greater than Ax, if there's a vector x such that x is greater than Ax, then I minus A inverse exists and is non-negative. So since In is greater than A dash times In, I minus A dash inverse exists and is non-negative. Using the properties of matrix and interchanging the transpose and inverse, we get I minus A inverse times its transpose exist. Thus, we can say that I minus A inverse exists and is non-negative. So we can see that if all the industries are profitable, then for a non-negative final demand D, there exists a unique non-negative solution to the input-output model and the total output X is given by I minus A inverse times D. Now this is not a necessary condition but one of the condition for the existence of a non-negative inverse. The general condition can be explained using Markov chain. So Markov chain basically has states corresponding to each industry and the transition value between them denotes the inter-industry coefficients. All the profit from the industry is assumed to be going into an absorbing state called the banking state. So coming to this example, looking at the coal industry, 40% output from the coal industry go to the electric industry, 30% goes to steel industry, and the rest of the 30% goes as profit to a banking state. So here, for the existence of the inverse matrix that's existing for the solution, the condition is that the associated Markov chain should be absorbing with the banking state as the only absorbing state. It means that there should be an overall profit from these industries for the economy. So we can say that if every industry is either profitable or depends on a profitable industry, then for any non-negative final demand Y, there exists a non-negative unique solution to this input-output model. So this is given by I minus A inverse times D. Now let us take an example of a matrix A, that is a matrix of inter-industry coefficients, where one of the diagonal elements is 1. In this case, it means that all the output from that particular industry is utilized input to that industry. That means that the industry consumes itself. It is neither profitable nor it supports a profitable industry. In this case, the inverse will not exist.
Let's move on to the dynamic input output model. The dynamic output model takes into account the rate of change over time of sectoral interdependencies. Now, what this means is that we can use this model to predict how the equilibrium rate of output will change over time for different industries. What we looked at earlier was the static mode of Leontief input output model, and this is a time dependent version of it. Now, we will consider the intersectoral model where we assume that n kinds of products are produced and used. Each sector produces only one type of product, and each product is produced in a certain sector. Let x of t be the gross output vector of the production sectors. It is now divided into two parts, y of t and z of t, where y of t is the vector of final product and z of t is the vector of intermediate product. Now y of t can further be divided into I of t and c of t, where I of t is the vector of investments and c of t is the vector of non-productive consumption. Now substituting this back into the other equation, we get x of t is equal to I of t plus c of t plus z of t, and this is called the dynamic balance equation. Now, the dependence of the intermediate product on the gross product is assumed in the form of direct proportionality. That is, z of t can be written as A into x of t. Here, A is the matrix of inter-industry coefficients. Now, the dependence of the vector I of t of capital investments on the vector x of t of the gross product is described by the matrix accelerator equation. So here B is the matrix of incremental capital intensity of production. That is, each element Bij in the B matrix describe the expenses of production of ith sector for increase in production in the jth sector. Basically, this B matrix denotes the ability of an economy to invest. Now, substituting all these equations and writing the final equation in terms of I of t, uh, we arrive at this equation. Now, to solve that final equation, we will assume that the intersectoral model is closed. That is, C of t is assumed to be zero. Now, we can solve this equation using the eigenvalue eigenvector method. The general solution can be written as such, where lambda k are the eigenvalues of the matrix Z and y of k are the eigenvectors. We have solved a similar problem in one of the tutorials. We can use the initial conditions to obtain the coefficients Ck's. Now we will look at some applications of the dynamic model. There are a lot of applications. Here are some of them. Governments can predict economic recession and take early action. The dynamic model can also be used in city planning. So for example, someone tasked with city planning can use this model to get the equilibrium output for the next 50 years and build infrastructure accordingly. So infrastructure built today will not be outdated in 50 years or won't be inefficient in 50 years time. Now let's look at investing. We can predict which sectors might be profitable and which won't be profitable. Even today, many trading firms and investment banks still use this model to make big business decisions. So that's it from us. Um, these are the references, and thank you.